Hello, Math 30-1. Welcome to Lesson 3B in our Travels Through Exponential and Logarithmic Functions. So in this lesson, we're going to talk about transforming exponential functions. First transformation we'll look at is not unlike what we've done with every other function we've done. So what about a vertical translation? What does it do? Well, given the graph, if you were to do +3, clearly it's going to move it up. And so if you shift it up, if k is greater than 0, it moves the graph up by 3 units. And obviously, you would take your point 0, 1, and that point 0, 1 would become 0, 4. The horizontal asymptote would also move up. And if we were to sketch 2 to the x minus 4, obviously it would move that horizontal asymptote downward 4 units. So it would be sitting on, and 0, 1 would become the point 0, minus 3. Horizontally, well, where would you see your horizontal shift? Well, you'd see it with the replacement of x with x minus h. So if I had 2 to the x plus 3, that would clearly move the graph left 3, and your points would become 0, 1 to minus 3, 1. And if it was sketching the graph of 2 to the x minus 4, that's a replacement of x with x minus 4, so that's obviously going to move it right 4, and those would be your transform points, right? So very similar to what we would have done with all our other functions in trig and so on, okay? So sketch a possible graph, come up with an equation or a graph that would follow the following characteristics. And this is where you could be asked on multiple choice, well, which of these graphs follow these characteristics? So what does it look like if A is greater than 0, but B is greater than 1? So it's a growth graph that's happy. Well, what does a growth graph look like that is sad? Well, it looks like that. What happens when B equals 1? Well, it doesn't grow at all. It stays as 1. What happens if A was greater than 0? Will it be a line of 1, but it'd be down at minus 1 because it was reflected across the y-axis. It was sad. And what if it's a decay situation? B is between 0 and 1, and A is greater than 1? Well, it would look like that. And if you reflect it across the x-axis, it would look like that, okay? In the next slide, we are talking about vertical stretches. So if you took our basic graph of y equals 2 to the x and you slipped an a value of 4 in front, clearly we know that that would have vertically stretched by a factor of 4. And therefore, all of our points should be 4 times taller. The x values stay the same and 4 times taller than they used to be. So that would be our new graph, and 0, 1, which is a very critical point, would become 0, 4. What if you sketch minus 4 times 2 to the x? Well, that would be a vertical stretch by 4 and a reflection in the y-axis, making my new point 0, minus 4. And very similar to what we've seen before, right? What if you had a horizontal stretch where you replaced x with bx? And I think we remember what we do, so you could complete this on your own and come back and look. So what if you have a 4x? Well, we should remember that that should horizontally stretch it by a quarter. So what does that do to my points? Well, as we talked before, it multiplies all the x values by 1 over b. So if I pick a critical point, any critical point, but we pick 2, 4, what would it do to the point? It would become a half and 4. And if it was negative, there it reflects it in the y-axis and also multiplies it by 1 over b as well. So 2, 4 becomes minus 1/2, 4. The y values are invariant and the x values are multiplied by 1 over the b value. Okay? And again, what I would like you to do here is to complete the descriptions, as you can see, are blank on your chart, and then come back here and check to see if you have it right. So in the first one, we have a horizontal stretch. Describe the following. And the vertical stretch, how does that work? And you can add the different notations that we might have had in our previous functions unit, transformation and reflecting. Well, if we see a negative on the outside, it reflects on the x-axis, and a negative on the x value reflects it about the y-axis. Vertical translation, the k-shift. And lastly, we have the horizontal shift, horizontal translation, which works on H. Okay. Applying transformations to different graphs. So consider this graph here. What is the base function related to that? Well, we can see it's probably going to be that 3x. That's the base. What has happened to 3x? Describe this sequence of transformations. So we can see it was vertically stretched by 2. It was horizontally stretched by a factor of 1/4. It was vertically translated 4 units down. And every point then can be described as x over 4 times x over 4, and the y values would be 2 times y plus 4 if you were to do mapping notation. We talked about that earlier. So now you could pick any point you have and map it to its new coordinates. So what would happen to 0, 1? Well, if you map it using this formula, you end up with 0, 6. What would your horizontal asymptote be? Y equals 4. And then on the next page, we can continue our work and describe, right? So you pick a few critical points from that original graph and map them on to the new graph to get an accurate graph of what this one looks like, right? And there's different ways that you could do it, but this is one way. Pick some critical points that you know are on the original graph and map them on to the new graph over here. The characteristics note is the domain still remains the same. The range is now y is greater than or equal to 4. The equation of the asymptote is y equals 4. And lastly, hard for you to see, but there are no x-intercepts, but the y-intercept is 6. So now that we've consolidated our transformation of these functions, use those skills to decide in this question what would result in the y-intercept being invariant. Which one of these transformations? So if the y-intercept is 0, 1, look at what the y-intercept would be for each of these. Clearly, the only one that stays invariant is y equals 2 to the 3x. Okay. If we would determine the value that's missing here, what does the point A9 on this graph? Well, if you put in A equals 3, 3, 9 would be a point that works here, and an A27 is on the graph, then the A value would have to be 4. Now you might wonder, well, how did that happen? The best way, and there's other ways you could use trial and error, but probably the best way to do it would be to say, well, if I've got A9, remember that this is x and this is y, so therefore in this case you need to solve the equation 9 is equal to 2x plus 1. That means that 2 to the x is equal to 8, and as we've done before, 2 to the x equals 2 to the 3, so therefore x equals 3. And you would do the same thing in question 2, where therefore if this is x and this is y, that means that you would have an equation of 27 equals 3 to the x minus 1, and you need to solve that for x like you would have done in lesson 2 of our travels, right? Now we start to look at some applications for this. So in this example, a population of 20 interrupts leaks, and the population triples each year for 5 years. You need to take information from contexts like this and be able to write equations. So the basic premise of all the work we've done so far is to decide, based on what's said here, what is A, what is B, what is T in this situation. So we need to make clear A is the initial amount of rabbits, B is the growth factor, and T is the time in years. So we can take this base exponential formula and pause. So as you ponder these questions, this is one way you can think. This B, that's the growth factor, well, if it actually is growing, multiplying by 1 keeps it the same. If you grow by a little bit, maybe it's 10%, but you're going to be adding whatever that percent is. Maybe it's 10%, and then you'd have 1 plus 0.1, so then the B value would be 1.0. Or if you were growing by 20%, it would be 1.2. So if you were not growing but decaying, so if your rabbit population was getting eaten too much and it was decreasing by 27% every year, then you wouldn't have a 1 plus, you'd have a 1 minus the amount. So it'd be 1 minus 0.27. So now your growth factor would actually not be more than 1, it would actually be less than 1. So it would actually be in this case, 0.73. So that B value can be whole numbers or it can be decimals depending on whether it's growing or decaying. So in this case, I'm going to sneeze. In this case, we start with a population of 20. That's my initial value. My growth is all about tripling, so it's 20 times 3 to the t. We substitute A and B there, and now 5 years from now, it will have tripled 5 times, so we get 4,860 rabbits. Wow, that'd be like Canmore, Alberta, where they got lots of rabbits. So there'll be about 4,860 rabbits in 5 years. And the next example talks about smoke detectors, and they are designed, right, like grass fires. So again, as we read these questions, we have to make sure we read carefully and understand the context. And so obviously there's this AM241 that has this half-life, and that's key as we're trying to discuss this. And so the average smoke detector contains this much, and we're trying to put this context into an equation that we can work through. So in this particular context, we weren't looking to answer a specific question. We were just trying to write a function that would model the decay of AM24. In this case, we start with 200, and it's decaying at a half-life, so our growth factor is a half, and it only does that once every 432 years. So it takes 432 years to cut that in 1/2. So you need at least that much, and to do it twice, if you wanted to have it cut in half twice, you'd obviously have to have 864 years to do it twice. But this is the equation that would model the amount of AM241 left in your smoke detector. Complete the assignment and we will discuss it tomorrow.